We have an expression for D that applies both inside and outside, but of course what we really want is the electric field, or maybe we want the polarization. So what we've got to do is just now use our definition of D. D is epsilon naught E plus P. So let's first look outside. So for the radius R greater than big R, also known as outside the dielectric, then D is epsilon naught E plus the polarization. What's the polarization outside? It's 0. There's no dielectric. We're outside the dielectric. No polarization outside the dielectric. So if we solve for E, we see that E is 1 over epsilon naught D. That's a D, not a P. And then if we just plug into what we had for D, we get that the E field outside the dielectric, R bigger than R, is lambda F over 2 pi epsilon naught R, which is exactly what we expect from Gauss's law for a line of charge, right? Lambda over 2 pi epsilon naught R, R hat. So our displacement field on the outside, everything worked out fine. Now let's look inside. R, little r, less than big R inside. All right, so again, we're going to say D is epsilon naught E plus the polarization field. Okay, well, let's solve for E. So E, bring it over here, it becomes, bring the P over here, it becomes the E field is 1 over epsilon naught times the D field, the displacement minus the polarization. And you say, okay, we have D. We got that from the little Gauss's law for D, but now we need a relationship between P and E. We are right back where we started with the slab. We know that the electric field creates some polarization, and the polarization reduces the electric field. Therefore, the polarization reduces itself, but that depends on the electric field. We're calculating the electric field. We're back in the circular loop. How do you figure that thing out? You could go with a microscopic theory, or you could just say this is a continuum. Let's just assign a variable to it. Let's do that on the next board.